JDSU, the world leader in broadband test and measurement solutions, and Frost & Sullivan's 2007 Test and Measurement Company of the Year, presents the Animated Reference Guide to Fiber Optic Testing. Let's start with an overview of optical communications. The principle of fiber optics is to transmit an optical signal through a glass fiber to a distant photoreceiver. The transmitter converts the signal from electrical to optical, and the receiver converts it from optical back to electrical. Single-mode fiber optics utilizes modulated laser diodes, pure silica glass, optical amplifiers, and photodetectors. The laser diode, or optical source, is a modulated pulse of light. Field measurements are conducted to determine the power and spreading of the light pulses as they travel down the fiber. There are two main factors that can affect the transmission of light in a single-mode optical fiber. Attenuation. As the light pulse travels down the fiber, it will lose optical power. Dispersion. As the light pulse travels down the fiber, it will spread, causing bit errors. Accurate testing and adjustments ensure that the optical fiber is capable of transporting the high bit rate for which it was designed. JDSU presents the drawing board. We will be using this board as a visual aid to introduce additional facts or to help you visualize a topic. There are several advantages of optical communication. A signal can be sent over long distances without the need for regeneration. The transmission is not sensitive to electromagnetic interference. Fiber optic systems provide greater capacity than copper or coaxial cable systems. The fiber optic cable is much lighter and smaller than copper cable. One important advantage of glass fiber is its ability to transmit light across a spectrum of wavelengths. This is known as dense wave division multiplexing. Dense wave division multiplexing, or DWDM, combines multiple optical signals at very high speeds onto one fiber, significantly increasing bandwidth. An optical fiber is composed of a very thin glass rod, which is divided into two concentric regions called the core and the cladding. A single fiber cable can then be coated with a protective plastic called a buffer and strength materials such as Kevlar and synthetic polymers. Multiple fibers can be bundled into plastic tubes called buffer tubes. This is one of many common designs used in fiber telecommunications. Buffer tubes are bundled together to create high fiber count cables that can be spooled onto reels of up to 30,000 feet long. Fiber cables can be directly buried in the ground, strung aerially between utility poles, or placed into flexible protective pipe known as duct or conduit. In a typical network, conduits are constructed underground in major cities, between major metro areas, and outwards from the central office. Back to the drawing board, we can see the average core size for a single-mode fiber is 9 microns. The cladding is 125 microns, and the buffer is 250 microns. To learn more about types of single-mode fiber, you can refer to the JDSU reference guide. Let's strip off the outer protective buffer and look at the glass itself. The fiber core and cladding have different chemical compositions which determine their index of refraction. The cladding, with its lower index, reflects the light back into the core. This effect guides the light down the fiber. If, for a moment, we could magnify a fiber and slow down the speed of light, we could visualize one pulse as it reflects off the core cladding boundary, achieving total internal reflection. The velocity of light in glass is different from the velocity of light in a vacuum. This ratio is known as the index of refraction. The numerical aperture of an optical fiber defines the range of angles over which the system can accept light. This is called the cone of acceptance. If light enters the fiber at greater than the critical angle, it is refracted and not captured by the core. If light enters the fiber at less than the critical angle, it is captured and guided down the core. Light is also reflected at the core cladding boundary. Propagation refers to light rays entering the fiber at different angles and traveling different paths or modes down the fiber, resulting in different arrival times. As an example, in multi-mode fiber, several modes of light are captured by a relatively large core. This has the effect of limiting the distance because of eventual signal delay. In single-mode fiber, only one mode of propagation is captured due to the design of a much smaller core. This allows for multiple wavelength transmissions and far greater distances. Mode field diameter is a measure of the beam width of light that propagates in a single-mode fiber. Effectively, light travels down the core and a small inner part of the cladding. Another angle illustrates the interaction of light between the core and the cladding. As the light signal travels down the fiber, it decreases in power, or attenuates. This can be expressed in a rate of loss known as dB per kilometer. In single-mode fiber, attenuation can be expressed as a unit of loss over distance, as in 0.22 dB per kilometer at the most commonly transmitted wavelength of 1550 nanometers. The scale of measurements in fiber optics ranges from the very small to the very large. It helps to understand the range of dimensions. For example, 1 gigabit is 1 billion bits. A single-mode fiber core has a diameter of 9 microns, or 9 millionths of a meter. An optical time domain reflectometer, or OTDR, can generate a pulse as short as 3 nanoseconds or 3 billionths of a second. Loss is minimal between 1310 nanometers and 1625 nanometers. This is where fiber optic communications is concentrated, also known as the telecom window. Let's take a look at a few of the causes of light loss in fiber optics. Absorption. Light energy is absorbed in the glass as it converts to heat. Rayleigh scattering. Light energy is scattered in all directions, causing loss of power. Since the light is scattered in all directions, a small percentage is directed 180 degrees back to the source. This, in fact, is what an OTDR measures. Excessive reflectance or high optical return loss can decrease the performance of a transmission system, eventually damaging the transmitter and decreasing the signal-to-noise ratio. Absorption, scattering, reflection, refraction, and injection loss all add up to build attenuation. These phenomena are inherent to the fiber. Now let's look at a few of the induced losses caused during installation. Large, noticeable bends and microscopic irregularities can both contribute to loss in a fiber. Core irregularities are another contributor to loss. There is always a component of loss when splicing fibers together. A fusion splice is created by joining two fibers together using heat. Non-reflective events can be displayed on an OTDR where there are no discontinuities or air gaps and are generally produced by fusion splices or fiber bends. A mechanical splice is a non-fusion splice where two fibers are cleaved and held in precise alignment. Reflective events can be displayed on an OTDR where there is a noticeable air gap and are generally produced by connectors or mechanical splices. Dispersion is defined as the spreading or broadening of light pulses as they travel through a fiber. The principal types of dispersion in single-mode fiber are chromatic dispersion, or CD, and polarization mode dispersion, or PMD. Chromatic dispersion is a measurable variation in the velocity of light by wavelength. The more variation in the velocity, the more the individual pulses spread, which leads to overlapping. Chromatic dispersion is expressed in picoseconds per nanometer of wavelength. Since glass fiber is extremely uniform from beginning to end, dispersion is proportional to its length, and we can define the measurement as a unit of dispersion by length. This is typically measured in picoseconds per nanometer per kilometer. Polarization mode dispersion is also referred to as the mean value of group differential delay and is expressed in picoseconds of delay. PMD also causes the pulses to broaden, increasing the bit error rate of the optical system and ultimately limiting the bit rate on a given link. The PMD limit is 10% of the bit time. At OC192, the limit is 10 picoseconds of delay. Fiber characterization is a comprehensive suite of point-to-point physical layer optical tests that measures and determines the quality and potential capacity of a fiber optic network. The suite of fiber characterization tests includes OTDR, power meter and light source, optical return loss, chromatic dispersion, and polarization mode dispersion. Let's take a look at each of the 5 tests that make up fiber characterization, starting with the versatile OTDR test. This test will take, on average, 30 seconds to perform. The OTDR, as we mentioned in Part 4, measures the backscattered light generated from a pulsed source. The data collected helps to identify several events caused by connectors, splices, and bends. Next comes the light source and power meter test. The light source will output a coherent wave of light over a few seconds. The power meter will record the power level at the far end of the fiber under test. The optical return loss test, or ORL, will simply measure the total amount of reflected light from source to receiver. The more light that is reflected back to the source, the less signal received at the far end. The PMD test utilizes a broadband light source and a receiver. Group differential delay can be measured over a short time period of 15 seconds. And finally, chromatic dispersion. One method of testing CD is to output 4 wavelengths of light and measure the delay at the far end. This is referred to as time of flight. All the results from the 5 individual tests can be compiled into a report that provides a comprehensive snapshot of each individual fiber that was tested. We all know about radar. Well, an OTDR operates on the same principle as radar by measuring the speed and power of a reflected signal. Instead of a reflected electromagnetic wave, we are measuring a reflected light wave. In fiber optics, this is referred to as reflectometry. Let's take a look inside an OTDR to see how it operates. The OTDR uses a pulse modulator and a laser diode for its source, and a highly sensitive photodiode detector as its receiver. As the scattered pulse returns to the OTDR, it is directed to the detector through the coupler, then amplified, sampled, and processed. This happens thousands of times per second to build up the signal-to-noise ratio. OTDR tests can be conducted from either end of a fiber span. Once a trace is produced by an OTDR, it can be used to measure such things as distance, location, loss, and reflectance. There are 3 main parameters used to set up an OTDR for operation. They are wavelength, pulse width, and averaging. The 3 most common wavelengths for single-mode OTDRs are 1310, 1550, and 1625 nanometers. An OTDR laser pulses. The laser is turned on and off for a very precise length of time. Time is distance. Turning the laser on for 1,000 nanoseconds will fill up 100 meters of fiber with light. A simple rule of thumb is, the longer the distance to test, the larger the pulse width to select. Let's take a look at a sample trace from a fiber 10 kilometers in length. Too short a pulse width will display noise. Too long a pulse width will wash out events. Process of elimination will help us choose the ideal pulse width. To understand averaging, we can refer to the Hubble telescope. The sophisticated camera on board the Hubble uses time-lapse photography to increase the signal-to-noise ratio of an image. An OTDR uses timed averaging to do the same. Power meters and light sources can be referred to as a loss test set. They can be used for complete loss from end to end, real-time power levels, and reflectance measurements. Meter operation is simple and automatic. In step 1, a reference is taken from the light source to the meter. In step 2, the meter records the power over the length of the fiber span. And finally, in step 3, the meters calculate the difference between the reference and the recorded power to obtain the loss. JDSU offers solutions for the network lifecycle, from R&D to ensuring quality of service, including a leading portfolio of installation, test, and monitoring solutions for fiber networks.